Some PhD students here? Oh, well, you don't count. Those two are my students, that's why I know them. Well, you count. Sorry, I certainly didn't mean to disregard you. So yeah, up front we had, the guys sent me a list of questions, which was 10 feet long and started from who are you to why do you do what you do and everything in between. So I'm very hard pressed to answer all those questions because that kind of is almost a ask me anything session, and I'm happy to turn that into an ask me anything if that is of interest to you. My problem is that I don't really know what you guys expect me to talk about or what you're usually talking about in these evening seminars. So please ask questions. Let's make that interactive, and I'm happy to adjust to whatever you would like to know about me. I don't know if it's so interesting to know anything about me, but about parallel computing, computing in general, high performance computing. C++, if you're interested in C++, hey, good evening. I'm closely related or closely associated with the C++ standardization process, the International Standardization Committee, so I'm kind of involved with that. So if anybody is interested in C++, I'd be happy to talk about these things. And on the slides I will have C++ code, because that's the only thing I can really relate with. I hate Java, just for the record. So don't ask me Java questions. You know more about Java than I do. I always avoided to have to do anything with Java. Yes?
What do you think about Python?
Python is a cool language because, well, that's an interesting question. What about Python? If you look at C++ and Python, these are kind of at the different ends of the language spectrum, right? You have C++ as a strongly typed, compiled, very fast language, which takes ages to compile, but the code runs very fast. And Python as an interpreted language, on the other end, scripting a nice REPL interface where you can very quickly develop your scripts, and you would think that they don't fit together. Actually, they fit marvelously together because there is a very simple way to integrate Python into C++ or C++ into Python. There are very nice language support in C++ for that, which allows you to develop your code in Python, and then you analyze and find out what is actually the slow part in my Python code, which object of my Python scripts or which Python modules are slow. So it's okay, I re-implement that part in C++, maintaining the interface, and all you have to do instead of doing import foo, you do import foo CPP, and your script will run as before. By the way, that's heavily done in systems like TensorFlow or PyTorch, these AI libraries that are so widely used nowadays. Part of that is just written in C or in C++, using that nice integration. So I like Python because it integrates very well with C++. Good question, excellent. Anybody doing Python? Who's not doing Python?
Nope.
Who's doing C++? Okay, good. Great. Glad to hear. Try to combine these two things. It's really fun. Other questions while we're at it? Anything that come up?
I heard of something called a Hive, which is possibly a new container coming in. What is that?
I have no freaking idea.
That's okay.
Never heard about that. Sorry. It's probably very similar to what Docker or these kind of systems do. Do you know anything about that?
No, honestly, I was looking up just because I knew that there's a new version of C++ coming out, maybe like 2025 or well, probably not 2026.
Yeah.
And I was wondering just like what they could have been adding, and one of it might be a new container
Ah,
called.
you mean, okay, you mean as a data type,
That's a data type.
not the compute container like
I
Docker or
have
something.
no
Sorry,
idea.
I misunderstood.
Couldn't tell you anything about it.
Well, a Hive data structure is a special data structure especially used for things like strings that allows to implement faster algorithms on strings because it puts some internal structure on the string representation. When you're looking for substrings and this kind of thing, Hives can be used for that. But I don't think it's part of the new standard. There is some discussion perhaps that, well, you can implement it yourself, but C++ is a language where you can do everything yourself in the end.
I guess so.
Okay, no, good question. Well, anyway, yes,
What is it that you don't like about Java that you do like about C++?
what I don't like about Java, I can't tell you because I don't know anything about Java. Well, the story is why don't I like Java? Let me try to explain that to you. Well, let me kind of get to it while I'm telling the story I want to tell anyway, and then I will refer to that at some point, okay? One of the stories I wanted to tell, I thought to tell you and to talk about today is that you might be interested in hearing, because I personally find it in hindsight to be educational and funny in some way, and it has in interesting ways shaped my research career, and that's why I wanted to bring that up here. Everybody knows what a German Frankfurter is? Frankfurter, these things you can eat. It's kind of a type of sausage, right? Mm-hmm. Yeah, it's lengthy, very thin, and very tasty sausages, which are made in Germany. And I'm German, by the way. You might already have noticed that. I had some videos on YouTube from the talks I gave, and one of the comments I got there, the content makes the German accent bearable. So please excuse me for my accent. I hope you can deal with that. Anyway, I grew up in East Germany, on the other side of the wall. So if there are questions about that, I'd happy to answer anything from that end as well. And we might have to cut out some things from the YouTube video in the end if I start going down rambling.
That's fine. We don't get monetized.
Okay, good. Anyway, yeah, so I grew up in East Germany, and one of the benefits of that was that I had the opportunity to do my undergrad in Russia, in St. Petersburg, at an institution which is kind of the equivalent of the US MIT. So it's a very prestigious institution. And by the way, I didn't pay a dime for that, which is kind of interesting from today's perspective and from your perspective. You're paying a lot of money to be here in one way or another. Anyway, so I did my undergrad there. And as you might already know, Russia, especially in the north, is very cold. It's a very cold country, very, very cold weather in the winter. Minus 40 degrees Fahrenheit is the normal thing in winter, with very high humidity. So when you go out on the street, you're essentially hitting an ice wall. Anyway, it was very cold. It was so cold that the water was freezing in the pipes inside the house. So we didn't have water, and we were hungry. And we said, oh, what can we do? We have to eat something. Well, somebody had that can of Frankfurters that I asked whether you know what a Frankfurter is, and said, okay, that's great. Let's eat some Frankfurters. And well, how do we heat these things up? We don't have water. We don't want to eat these things cold. So, and since we were kind of electrical engineers, somebody came up with the idea, well, let's plug it into the receptacle, right? Just take a cable, receptacle, Frankfurter left and right, and guess what happens? The thing exploded. Obviously. We should have expected that, obviously. So, but since we were, well, you know, students, when you had a beer or two, you start getting crazy ideas. So we said, somebody came up with the idea, hey, we should probably measure and collect the how much current is flowing when we change the voltage we put on that Frankfurter, right? So if you think about that Frankfurter, right, that kind of sausage, and you have your receptacle here, you don't want to connect that directly. But what you want to do, you want to put a kind of resistor here. You can regulate, so you can control the voltage. And then you put a measurement instrument here, which was measuring the current flowing, and we were measuring the voltage over the Frankfurter. And then we were slowly increasing the voltage, and we're measuring things. So what we got is a kind of dependency of the current over the voltage. And we were collecting things. So we started with 0. 0 was fine, right? Nothing happened. Then we increased it a bit, and it went up, obviously. And it went up, and it went up, and it went up. At some point, strange things started to happen with that voltage, because what we are seeing is that suddenly the current was dropping down. And then the current went up again. Well, and in the end, the whole thing was exploding, right? Obviously. But if you think about that, what does that mean if you have this kind of type of curve, this kind of dependency? Or let's ask the other way around. What is the gradient on that curve? It's delta I over delta U, right? What is this? Conductivity. No, yeah, conductivity, right? So this gradient gives you the conductivity of the Frankfurter. And what is 1 over the conductivity? What is 1 over? Well, this is C. What is 1 over C? The resistance, right? 1 over conductivity is a resistance. And that means that in this range here, we got a negative resistance. So we were happy. We said, oh wow, we will get the Nobel Prize. We found a way to get negative resistance out of it, because essentially negative resistance means you get energy out of nothing, right? If you think about it. And well, nowadays we know how to do that, actually, at least on the semiconductor level. There are certain semiconductor elements that use tunnel effects, which causes that kind of negative negative resistance effect. But we didn't expect to see that was a Frankfurter, right? So sadly, as you might already guess, we didn't get the Nobel Prize for that. Why didn't we get the Nobel Prize for that? Anybody? Can you guess why? What did we measure? If you think about it, what we were measuring is, and we were just stupid students with too much beer in our blood. So what we were measuring essentially were, or what happened when we increased the voltage, the Frankfurter slowly was heating up. And that means that we're actually measuring data points on different temperature curves, because the resistance of that Frankfurter obviously depends on the temperature of that thing, right? The higher the temperature, the less the resistance. So what we were measuring, essentially, if that is T0, that's T1, T2. So we are measuring data that was completely unrelated, because we should have waited for the thing to cool down before doing the next measurement. Then everything would have been fine, and we wouldn't have seen that negative resistance. Make sense? So, what's the morale of that, and why I'm telling you that story? Not because exploding Frankfurters are so funny, but what I want to tell you is that when you do research, and especially the graduate students that do research, you might sometimes come across things that are unexpected. And there could be two reasons for something to be unexpected. Either you are really onto something, like Einstein you know, when he came up with the relativity theory. But most of the time, you're not discovering anything. Most of the time, you're screwing up. And I want to kind of highlight that to you and tell you, be very, very careful with these conclusions when you're looking at things and suddenly you don't understand what you actually see. Most of the time, it's your fault that you're measuring things badly. Reminds me of that paper, I don't know, 15 years ago. There was a big paper and big boom because some guys in CERN discovered that neutrinos could move faster than speed of light, right? I don't know if you remember that. You might have been too young for that. It was a big discussion in the community because nobody could explain that, why the neutrinos were moving faster than speed of light. But nevertheless, 10,000 people were authors on that paper in the end because everybody wanted to be part of that paper. I mean, later, a year later, they figured out what was wrong. It was a bad contact on one of the measurement instruments they were using for that. But it took them a year to figure that out. So you might want to write a paper about this, right? Because you might find 10,000 other people who are interested in being part of that paper because they want to be famous. But most of the time, you should think again when you see that. That's one of the conclusions, one of the things I wanted to tell you. The other thing I wanted to tell you, and especially again for the graduate students who want to do research at some point, research is something, it's a process that is very tedious and very slow and very incremental. As I mentioned Einstein, right? And he kind of, the story says that he was walking around all day long doing nothing, apparently. Well, he was thinking. But he was thinking very hard. And he made the impression that he's just going out for a stroll in a park or doing something. But in the end, he came up with a one-page PhD which revolutionized physics. This is not what research normally is. While thinking is something you should do, obviously, but research is most of the time a very incremental, very slow process where you move from one insight to the next, and the increment between these insights is just minimal. And only after a certain amount of time, after a year of work, after 2 years of work, you suddenly have the breakthrough and you get to something where you can say, oh, this is new, okay? And most of these increments are in your brain because you have to understand what you're doing actually and why things are happening. Okay, that's just a story. To tell you about Java, East Germany, right? After the wall came down in '89, the whole society in East Germany went to crap. So, I don't know what the right word for that is. It's actually the appropriate description of it because, I mean, 50% unemployment rate and all academic institutions were kind of killed and yeah, it was a very bad time. During that time I was unemployed for a couple of years. But the society or the government has provided support for those people in one way or another. Well, they had to eat something. And one of the things you had to do in order to get the support is to go to courses, to learn new things so that you're prepared for different jobs. Not that I wanted to do something different because I loved C++ at that time and I wanted to do that. But they sent me to a Java course. And you know, that connection and that environment probably has caused me not to like Java. The other thing was that when I was sitting in that course, the instructor knew less about Java than I did, even then. And whenever I wanted to do something with Java, I felt that both my hands are tied behind the back because I was used to C++ and I knew how to do things with C++. One of the things that bothered me with Java is, well, if you know C++, you might know that, well, let me ask the question, what is the most important feature in C++? Anybody?
Like pointers?
Well, that's the least important one. You don't need pointers when you work with C++.
Being more general, user access over memory?
Yeah, you have full control over memory, yes, and that's part of it. The most important feature in C++ is what's called a destructor. Right? Well, I told you, right? You were sitting in class, and you might remember that. And the destructor is a function that the compiler automatically calls when an object goes out of scope. It's kind of similar to a finalizer in Java, but in Java the finalizer will be called when the garbage collection invokes it and deletes the object, but in C++ this is very deterministic. Whenever the object goes out of scope, out of the lifetime ends at the end of the curly brace, the destructor will be invoked automatically. And that allows you to do things like creating an object and a scope that opens a file and never close it, because the destructor of that object that represents a file closes the object behind the scenes for you. So you never have to worry about cleaning up after yourself. And I was missing that feature. I never understood how I can write code in Java that does that for me, right? Deterministic destruction. How do I close a file in Java deterministically when I exit the scope without explicitly putting a close function in each and every place where the function exits? Is there a way to do that? Well, teach me. As I said, I just don't know. So, and I always felt, no, I can't do that. I can't live with that language. And since then, I decided I will never look back. So sorry for that. Can't give you any better answer. I hope it makes sense. There might be a connection to that situation I was in at that time. And I'm projecting nowadays. Good enough. Okay. Remember the Frankfurter. Whenever you come across something you think you are close to a Nobel Prize, you're probably not. Well, there are other people who thought that they would get the Nobel Prize, right? Just recently, and they didn't get it. But that's a different story. And you probably know whom I'm talking about. Okay.
You mentioned using C++ 30 years ago,
Yeah.
or even before that.
Yes?
And you're still using it now.
Hmm.
Has anything changed?
Oh, well, yes, absolutely. Absolutely. I mean, the language is completely different from what was available back then. And especially things like, well, C++ 11, the language that was standardized in 2011, has made a big change to it. It made it more almost Pythonic. So you can write code that looks almost like Python code, and very, very clear way of writing things. And especially it has helped to get rid of pointers in the daily use. And I believe strongly that whenever you want to write a pointer in your code in C++, you should think again and just not use it, because you can do it without pointers just fine. Why am I so adamant about pointers? Anybody? I mean, you suggested pointers. You probably know something about pointers.
I'm very beginner, but I just know that that's one of the things that is taught in a lot of beginner C++
Okay.
courses.
Well, that's beginner C code, right? There you have to use pointers. Without pointers, you are kind of dead, because there is no other language facility. But in C++, you have language facilities that replace the use of pointers. The problem with pointers is not that they are there, and it's not that they're a bad language feature by design. They are absolutely necessary, because when you want to refer to memory, you have to use addresses, right? You have to kind of identify a variable using an address. And the pointer is nothing else but an address of the variable. So it's kind of essential and built into the language. But the problem is when you write a function which hands you a pointer, right? You have a function that returns a pointer. You only see the pointer. You don't know, do I own that thing now? Or is a function making sure that the memory is deleted at some point? Or am I one of 10 places where that pointer is being used and somebody else is taking care of it? Just from the interface, you can't see the semantics of the use. The ownership of the pointer is not clear. And that is the biggest problem that causes a lot of problems in daily programming, because it's almost impossible, especially in parallel programming, to always know when should I delete or when should I free memory. In Java, you have garbage collection, right? There, you do that. In C++, you don't. So you have to use different language facilities which facilitate similar things that allow you to forget about deleting memory. And they use what's called a smart pointer. It's essentially just an object which carries the pointer around, but takes care of the free of the memory at the appropriate time. So you don't see pointers anymore. Okay? That is the reason why I'm saying you don't need pointers. And don't use them if you don't absolutely have to. Other questions? No? Okay. Well, then I want to ask a question to you. I asked in the beginning about computer science. Who's a computer science student? And who not? What is computer science? What is the essence of computer science?
Study of what can be computed.
Close, yes. Other opinions? What is computer science? What is the essence? I mean, computer science as a name is a horrible name for what we do, because it's neither about computers nor it is a science. Right? It's neither of those. So in that regard, it shares properties with. Well, let me put it that way. Computer science is as much about computers as astrophysics is about telescopes and biology is about petri dishes. And that is probably because, and that's very characteristic for very new sciences, and computer science is a very new science, right? It is barely 100 years old, not even 70, 80 years old. In these new sciences, when people actually don't know what they are doing, they tend to name the thing after the instrument they use to perform what they do. That's why they say computer science, right? Because they use computers to do what we want. But in actuality, it's not that, right? By the way, computer science shares that property with another very widely and very old science, which is geometry. Geometry stands for, and Panos can tell me better because he's Greek, that it stands for Gaia and metros, right? It's the earth and measure. And the name was created. Is that correct? Yeah. Thank you. I wasn't sure, but okay. But it was created by the old ancient Egypt 2,500 years ago, because they had to restore the borders of their fields after the nearly Nile floods, right? The Nile was flooding their fields, and they have to kind of reestablish the boundaries of their property. So they created the tools that they needed to survey the boundaries. And that's when they named that thing geometry. And it's very similar, because at that point, all geometry was all about was measuring things and surveying the earth. Now, on the grand scheme of things, you could even say that we today know less about computer science than the old Greeks knew about geometry. We know today that geometry and the Greeks, what they have actually been doing, they have been laying the foundation for our understanding of space and time. And in some sense, the foundation for all of maths, right? Geometry is kind of the fundamental things where all the maths come from. In a similar way, people 200 years from now, they will look back and say, oh, those primitives in the 20th, 21st century, they actually didn't know what they were doing. And they had these strange gadgets, which they called computers, and that's why, since they were using those computers to do things, they called what they are doing computer science. Just to give you an example, if math and geometry, and we know today that math came out of geometry, if math is a science which is all about stating facts, right? It tells you what is true and proves what is true, then computer science is all about how do we get to that truth. And that's why your suggestion that it's about how to do things is correct, right? It kind of encapsulates what we do. Just to give you an example. So math says that y is the square root of x. What does that mean? What does it mean if y is the square root of x. It means that, well, x is larger than 0 and x squared is equal to y. Or the other way. Yeah, sorry, the other way around. Y squared is equal to x, right? Yeah, x. This is math. This is a fact. It states what is a square root. On the other hand, if you go to computer science, how do you compute a square root? How do you do that? What is the process of producing a square root? Anybody?
You do a bit shift to the right.
Okay, a bit shift to the right, and then that divides by 2. Doesn't give you a square root.
You would just check different numbers until you find a square.
Okay, fair enough. That might
But
take
it's
a while,
hard.
right? But
His is
yeah, you're kind of right, because it's in the simplest case a repeating algorithm. It is actually a fixed point algorithm. Anybody has tried to compute the cosine on your calculator? Well, nowadays nobody has calculators anymore, but on your phone you have probably something similar to a calculator, and if you take an arbitrary number and compute the cosine of that and repeat computing the cosine from the result of the previous operation, you will see that it will converge to a constant number. So it will converge to a number and will not change anymore after, I don't know, 50, 60 cosine of computations. And that's called a fixed point function. Okay? Computing square roots is very similar. And that is an algorithm that was developed by another Egypt mathematician. I just forgot the name now. Much later, not the ancient Egypt, but a later one. Essentially what that algorithm says, well, you want to compute the square root of x, so you take a guess, let's call it g, and then you compute the average of g and x over g. And that gives you a new guess, and you repeat that process over and over and over again. And that makes sense, because once g is the square root of x, you get square root of x equals average of square root of x and x over square root of x. And this is square root of x. Okay? So it's obvious, right? So once our guess becomes square root, the whole equation is true and it will not change anymore. The more we can compute that over and over. So you see that we have on one hand the fact of the math, and on the other hand the process of computing square roots. Now, if computer science was all about computing square roots, we wouldn't be here, right? It would be too boring, this thing would be done, end of story. So what is computer science actually about? Computer science has to deal with humongous amounts of code in the millions and billions lines of code. That means these computing software systems are highly, highly complicated, highly complex. So I argue that computer science is the science of managing complexity. So we are developing methods that allow us to work with these large systems which nobody can hold in their head anymore in one go. Now you might say, okay, that doesn't sound right. I'm an engineer, I'm building bridges. My stuff is very complicated. Another person comes along and said, hey, I'm building planes. Very complicated systems. You wouldn't be able to build these systems without being able to abstract subsystems, right? So you can reason about the control system, about the engines, about gas supply, and so on and so on. But the difference between all the other engineering disciplines that work with very complicated and complex systems and computer science is that we as computer scientists are not limited by physical limitations, right? an electrical engineer, when you build a amplifier chain, you have one amplifier, everything's fine. You add a second amplifier, works. But once you come close to the thousandth amplifier, the whole system becomes unstable because the thermal noise from the first stage of the amplifier takes over the last stage just by being amplified over and over and over again. So and computer science doesn't have to deal with physical limitations. All we are dealing with is time limitation, which is serious. That's why we want to avoid very complicated algorithms with bad computational characteristics, right? O(n) squared algorithms are bad because they take a long time to compute. Or NP-complete problems are even not computable because they're so time-consuming to compute. We don't want to do that. But that's the only limitation we have. All the other limitations are purely what our mind can create. How complicated can we build the system? And we can build abstractions over abstractions over abstractions. And that's why the software systems are so large, like no other system we have around. Right? Billions of lines of code. Just the operating system we have is 100 million lines of code. And that is just the fundamental, the foundation of what we are doing. I don't know how many lines of code Google actually has. It's probably in the billions, really. So that's why, just take away, computer science is a science of building abstractions and managing abstractions. Now the last question I have, well, the next question I have is, what are the two most important abstractions we build in computer science? And you were very close with your Hive question, by the way.
Wait, is that a hint?
Yeah, well, it's a hint, yeah, sure. What are the two main abstractions we build in when we do programming?
Data structures.
Data structures, right, is one. And the other one?
Algorithm?
Algorithms, right. Algorithms and data structures. And there was a book 50 years ago, Niklas Wirth, the inventor of the Pascal programming language, you might have heard of Pascal, who has written a book which was titled Algorithms plus Data Structures equals Program. And that is what the whole thing is about. And when we build data structures, we abstract complex description of the reality. And when we build algorithms, we abstract ways of computing things. And these two things taken together gives you programming. And all what computer science does is enable programming on arbitrary complex levels. Make sense? Any questions about that? I know you're probably not here to hear these stupid lectures about these trivial things, but I believe that is, well, it's almost the only thing I can give you on your way as a researcher or as a programmer, that you have these basic understanding. What is it we are doing? I mean, you are a computer engineer. Do you feel, or you are a computer engineer? What is computer engineering about?
It's a way to combine, in my opinion, a way to combine our computer science principles into electronics.
Okay, fair. So you're in the fast electrons, or are you on the slow electron side?
Let's say slowish.
Slowish, so the grid, power grid, and this kind of thing? Okay. Well, yeah, sure. Nobody says anything against my thesis?
I noticed that like data structures and algorithms, I feel like they just like become a way just to get a job. Like, have you heard of LeetCode?
Or what?
Do you know what LeetCode is? Like,
LeetCode?
yeah.
Well, yeah, sure. It's kind of.
I don't know. I feel like you said like it's so important to know like data structures and
Yeah.
algorithms, but I feel like people just see it as a ticket to get into a job, and like then they just forget about it afterwards.
Well, that's stupid on their part if they forget about that.
Well, not necessarily forget about it, like think about it.
Look, if you have well, especially in C++, which C++ has a very powerful standard library, and that standard library has essentially 150 algorithms, very simple ones, starting from for each to more complicated ones like sort and reduce and scan-based algorithms. on one end, and on the other side, a set of containers, which are the data structures. Things like arrays, lists, maps, hash maps, all these things. And the beauty of the standard library in C++ is that containers and algorithms are completely independent of each other and orthogonal. You can use every algorithm with every container, and when you come up with your own container, you can still use the algorithms with your container as long as your container is built in certain ways. And on the other hand, if you come up with your own algorithm, you can use it with the existing standard containers in a very flexible way, very orthogonal. That's the other thing that I don't like about Java, because every data structure has their own algorithms. There's a list sort, there's an array sort, there's a hash sort, there's a map sort, you know. So you have n times n implementations of the algorithms, and the number of data structures, and n the number of algorithms. Whereas in C++ you have n plus n number of things, because you can orthogonally combine these things. By the way, the standard library, C++ standard library, especially the container and algorithm part, is one of the most ingenious pieces of engineering mankind has come up with, I believe. So the people behind that are really geniuses. They have created something which is just mind-boggling. And if you don't use that, or use it only to get into a job and then forget about it, well, then you will not stay long in that job, I'm sure. On the other hand, if you know it, you will be the king of the tribe, because you will be able to write code easily. Because, okay, you have a problem, you want to do something, so you come up with a data structure, you come up with the algorithm, and then you throw it together and go home. End of story. Right? You don't even have to think about that anymore, because you're building abstractions on a very high level, which combine very nicely. And otherwise you will fail. Other questions, other comments? Come on, argue with me. I'm
Huh? I remember reading about a certain category of algorithms that were popular, I think, in the 90s called evolutional algorithms. So it's a category that I think tries to mimic evolution. I was wondering if you have any experience or looking into those, or just...
I have not. I haven't done anything with evolutionary algorithms. I can't tell you too much about it. Do you know where they have been used?
I believe they were used, so like when people were initially kind of sketching neural networks, that's what was one of the techniques they originally used, just because it's a great way to mimic crossover or some aspects that kind of...
Well, in some sense, what we do with neural networks nowadays are just evolutionary optimization problems, right? And all the algorithms to train these things are in some sense evolutionary, because they make the data structure evolve over time. So you can narrow down the coefficients of the parameters on a neural network. So, but I don't have to work with it. I can't tell you anything about it. You don't want to have pizza. That's a good part to be a speaker in this kind of thing, because nobody will run away, because everybody wants to have pizza. So yes, please.
I was wondering, what's your introduction to computer science? And I'm wondering, like, when you got introduced to computer science, what made you dive deeper into it?
That's a good question. There was no single event that I could say this has triggered going deeper. It was perhaps the moment when I came here to LSU, when I was working in industry for 15 years, essentially creating software on a, hey, do this, do that basis. So there was not much of involvement. It was fun, it was okay, but it wasn't going very deep. I was just doing what I was supposed to do. And after coming here, I was a researcher here at LSU. Came here in 2005. And at that point, the picture changed, right? Because well, as a researcher, you're kind of interested in exploring the boundaries of what you're doing. And that, and collaborations we had at that time with people who were older than I and much more wise than I, has helped to get into things a bit more closer. But in the end, it's just a shitload of work. So don't expect that to happen overnight. will take a while. And just for the record, Panos said I'm working with C++ since for 35 years now, and I still believe I don't know the language. Funny story. I always asked students or people who want to work with us, hey, what do you think on a scale from 1 to 10, what's your knowledge of C++? And I usually get a 5, no matter whom I talk to. Even if somebody had just one introductory course in college, they tell you, yeah, I know 5. I know as much. On the other hand, when you ask the inventor of C++, Bjarne Strustrup, what do you think your knowledge about C++ is? And please note, he is really the guy who came up with all of that. Well, he said 7. So C++ is a language you will learn for a lifetime, and you will never be able to know the whole thing. And that makes it so difficult for people to get into it, because it's a very large language, very complicated. Yeah, sorry, I can't really answer your question about what made me do that. It's more of the opportunities, right? When you're busy and mentally busy with doing things every day on a routine basis, it's much more difficult to get deeper into things than when you have a bit of leeway as a researcher at the university. Yeah. So get a job as a researcher. That will help. Are you planning to go into academia, or do you want to go to California and make the big bucks?
After this semester, I plan to go to New York.
Oh, well, you can make the big bucks there as well. There's Bloomberg, and there are all these big companies are in New York, so you'll find a job. Okay.
Well, I have a
Yes.
Do you ever lose motivation in doing learning computer science?
Good question. My recipe not to lose motivation is to work with students, because I'm getting old, and it's harder for me to do things, especially context switching is much harder. You will notice that when you get older, that doing one thing now and another thing 5 minutes later is somehow very difficult. But the experience combined with that high context switching or low context switching overhead of students is very productive. Right? So students, they don't need sleep. When they're interested, they start just working and going forward, and they don't care about time and whether it's in the middle of the night or anything. And I can provide the experience, right? The knowledge I collected over time. So in that combination is a very fruitful combination, and I love that. So I have no problem with losing motivation, not now at least. I love what I do. You had another question?
What year did you do computer science undergraduate?
85.
For 1985, was computer science like a big field? Maybe not as big as it is now, but
well, I didn't graduate as a computer science. Computer scientist. I graduated as a what they called cybernetics and database person. So it was only in the beginning back then that computers started to play a real role. So there was no computer science department. It was more of a let's do something with the computers.
what interested you in this field compared to electrical engineering?
You know, programming is a very satisfying exercise. I don't know if you ever felt that when you're writing some code and you're beating your head against the wall and you can't make progress and it doesn't work, and you try this, you try that, and nothing really works. And then suddenly it starts working. That feeling of elation is just, it's better than chocolate. So it really gives you a lot of dopamines and helps moving forward. I don't know if you experience that, right?
Sure. Sorry, I wasn't raising my hand, but I totally agree.
Yeah, you agree, right? So, and that feeling, that state of mind is just what helps me get going and keep going. I don't know, if you haven't achieved that, you really should try doing that. If you have a particularly hard homework, right, you sometimes might have felt that. And by the way, if you want to get a bit harder homework, I'm teaching operating system next semester. Will be there?
I'll try to be.
Good. Come by. The homework I'm having is challenging. And it will give you that feeling in the end. That if you, oh, I accomplished something, great, super. So it's not just, write a piece of code that reads that data from here, does 3 for loops and writes it back out, right? Nobody cares about this. Coding is a very, very productive, very satisfying exercise. And that's how I feel.
So I know a few of us here are currently pursuing math minors or have math as a second concentration. So I wanted to ask, what math courses or topics do you think have the most overlap or benefit towards just computational thinking, algorithm vision?
Okay, fair. The thing is, math is a science which is 2,000 years old, at least, if not older, right? Ancient Egypt's 2,500 years. And humanity has come up with a very solid science or system of axiom, is an axiomatic system that allows to build or describe essentially everything we know about nature, because it gives us the formulations for that and so on. And math is so interconnected that you can come from different angles and you always end up with the same thing, right? That Euler's equation, right? E to the power of I times pi equals 1, which is, you ever heard that?
I think it is.
E to the power of I times pi is 1 or minus 1? I forgot. Anyway.
I think it is 1.
I think it's 1. So just imagine E and pi, two irrational numbers, and I as the complex, the square root of minus 1, combined gives you 1. So that alone tells you how perfect math is, how beautiful it is, right? Because it combines all that in one formula. So just to answer your question, I believe there's a very deep relationship between writing code and math. A very deep relationship. Yes?
Sorry, it's actually +1 equals 0.
Yeah,
It's
it's minus 1. It's negative 1.
It equals minus 1.
Yeah.
So, yeah. Sorry.
I messed up.
But it's beautiful anyway.
Yeah.
So there's a very deep relationship between concept that math has developed, abstract algebra concepts, category theory. So very abstract things that have a direct relation to coding. If you have worked in C++, you might have used templates. So templates are a mechanism in the language that allow you to tell the compiler how to generate code from a set of types. So you give it a function, which is a template function. So the function itself is not a function yet. It will turn into a function the moment you call it with an integer, or with a double, or with a string, or whatever. And the compiler uses that type information of the arguments to actually generate the correct function for those arguments. Now, the templates, the function might not compile because, well, it might do A plus B. So that's right. The code. Let's do a simple template function. And the syntax is weird, so I apologize for that. Type name T, and then let's say how to add TA, TB, and all it does, it adds these two numbers. Return A plus B. This is a template function you can use with any type that supports addition. Integers, doubles, strings. If you have a type that supports addition, you can use that function with. Now, but as I already said, T needs to support addition. It needs to have certain properties in order, that type has to have properties in order for this function to compile. Now, if you go to math, it tells us that T has to be a commutative additive ring. If you ever heard what that is in maths, it's a category theory, comes from abstract algebra, where they have developed that system of axiomatic system of sets with certain properties. And there is a connection between math and computing. Because if you know what math gives you in terms of reasoning about sets, you can immediately reason about types. And the important thing why I'm saying that is, if you can write a function and you know that it will work for additive commutative rings, then you can be absolutely sure it will work for any type that has these properties, even if that type will be invented only 10 years from today. Yeah? And that is the power of the connection between math. So there's a very, very deep and very, very abstract connection between computer science and math. So absolutely, do some math, especially these abstract parts of math when you want to do programming. Make sense? So they really ran away. Or are they going to get the pizza?
That's what I thought.
They're going right now.
Oh, okay.
So
Yes.
does HPX also have like a very theoretical and like beautiful background? Like, you know what I mean?
Yeah, sure. Well, we get to HPX. And I don't know if you really want to hear more things from me. I'm happy to talk about HPX and parallel programming a bit. I have a couple slides prepared. If you're interested, I don't want to bore you. And I know that I'm in between you and pizza, so please stop me. We can talk about HPX. But the main idea behind HPX is that we have built the APIs, the abstractions of HPX after the C++ standard library. So yes, there is a deep connection there. But we have not come up with those, at least not completely. We have come up with some of the abstractions, but mostly it's C++ standard. That's why. We didn't have to think because other people have invested the time. Yes?
So I kind of want to expand upon templates. So
Yeah.
I did read somewhere that their templates in and of themselves are Turing complete.
Yes.
And that kind of leads me to think that they have a lot of applications in areas like high performance computing. So just from your experience, have you seen any like specific applications that you find interesting for templates in that field?
Turing completeness. You know, everybody knows what Turing completeness means? No? Turing completeness means that you can compute anything. You have all the facilities you need to compute anything you want. That's essentially, in the essence, means Turing completeness. So, and the thing is that templates as such are Turing complete. And that means that you can do computation at compile time, not at runtime. Normally you compile things and you run your program and the program is doing the computations. But since templates is a pure compile time feature, it's not a runtime feature. It's happening when the compiler is generating code. You can use templates to do computation at compile time. Okay? And that means that you can use that facility to build optimal code, because you can use type properties to decide which of the code snippets you have prepared will be used in a particular context. Well, in this case, you might have a special add function that works particularly efficiently with strings. And you have another add function which particularly well works with integers, just hypothetically. And then you can let the compiler decide which of the two to use depending on the arguments you supply. So you can use templates to control how code is being generated and which of the... You can compose code such that you get optimal execution times by using templates. And that's where templates come in. And not only in high-performance computing, general computing, you can use it everywhere.
So as far as I can like understand, it sounds like you can use templates. It makes decisions. It's like,
Well, you can let the compiler make decisions based on type properties.
right.
So-
How, but doesn't there have to be a certain amount of looping or some other features? Or
Not necessarily, right? What is a simple example I can show you?
a decision.
I don't want to overwhelm you with complicated looking syntax. but you can compute. Well, the first example somebody came up with, and that was kind of a horrifying revelation for everybody in the standardization committee. By the way, do you know where templates come from? Templates were developed when the standard library was, when the containers and algorithms were added to the standard library. And the templates were specifically developed to support that orthogonality between algorithms and data structures. And after they have come up with all of that and had standardized things, only then somebody came and said, you know what, you can compute prime numbers at compile time. You can give me all the prime numbers at compile. And the first version of that code was essentially a piece of code which generated an error message because it was broken in terms of syntax. But the error message gave you the list of prime numbers the compiler had computed. And at that point, everybody said, oh shit, what have we done? Because they have added another Turing-complete language to the language that already is Turing-complete. And everything comes from there. So you can compute numbers, you can make decisions on type properties, you can do type computations. You can turn one type into another type if you want. In the simplest case, if you have a t, you can turn that into a t star, into a pointer to a t. Or you can say, okay, if this is a t star, give me the t that is underlined, and then do things with that type that is behind it, and so on and so on. So you can do code and type transformations that allow you to optimize code. And if you're really interested in that, just come along. We can look at HPX. There's plenty of that there. And you can just experience it for yourself. And ask Panos and City. City probably rips her hair out currently because she is kind of trying to get into that. You might want to tell us about your experience with that. You might just tell everybody don't do that or something like this.
No, I wouldn't say that.
Okay. Well, I can leave the room then you can say it.
No. HPX definitely, if we have no idea about C++, then I think it is very difficult. If someone has some background with C++, I think it's not very difficult to start.
Yeah.
But initially,
it's a steep learning curve.
Yeah, you need to be aware that it's not going to be very easy. But once you start looking at the code and try doing something with HPX, it gets easy.
Okay. So should I talk about parallelism a bit, about HPX? Are you interested in that? Yeah? So stop me if I'm kind of... just be warned, when I start talking, I can't stop. That's why. So whenever you say, I want to get my pizza, just raise your hand and say, shut up. Okay? Well, let's do that. I'll try to be quick, to give you a quick overview of what you said. Just, you know, one of the questions you gave me was, why do you do HPX? Why do you do high performance computing, and what's so special about HPX? Why do you do all of this? And I want to give you some hints where that's coming from. So, if you look at parallel applications today in the wild, so HPX is about parallel computing. Right? So it's a library that gives you facilities that enable you to write code that runs in parallel, which runs faster than if it was running on a single core. If you look at the landscape outside of HPX, in terms of parallel facilities, you see this. You see OpenMP. You might have heard of OpenMP. It's the widely used parallelization framework for on-node parallelization. It's around for 50 years now. It even works in Fortran, just to give you an idea how ancient it is. There is OpenMPI, or MPI, as a facility that allows you to do distributed computing on big clusters, on supercomputers. There's CUDA to do GPU programming. You have heard of CUDA, right? Probably everybody has heard of that. There is CUDA for GPUs that are produced by NVIDIA. There is HIP, which you use to program GPUs that are produced by AMD. There's SYCL, which you use to program GPUs that are produced by Intel. So in other words, we have a variety of different solutions out there for different types of parallelism in our systems. And these things don't work with each other. They are around for a long time, but they never manage to really coordinate between these different types of parallelism. In terms of interface, in terms of mentality, in terms of how you write code, in terms of how you reason about code. So it's completely different things. And has anybody been doing GPU programming? No? It's completely different from what you know from normal CPU-based programming. And that's why this picture, right? It's a big pile of tools you have, but you can't combine them. You can't really build things out of them in a coordinated way. That's one reason why we came up with it, or why we thought it might be a good idea to create one library that allows you to use the same API, the same mindset to work on these different platforms. From the laptop to the big supercomputers, from the GPUs to CPU parallelism and so on. Good question? The other thing, if you look at this is the trace of a application that is supposedly very well parallelized. So each of those horizontal lines represents one CPU. The green blips mean that the CPU is doing something, and the white blips in between the green ones means that the CPU is not doing anything. And that is what you normally see when you look at parallel libraries, at parallel applications today. The reason well, especially for the second part, that might not be obvious to you. You might say, okay, that thing is parallelized. Why are all the CPUs do stuff at the same time? Why are those gaps in between? Well, the reason is that when you have a loop, most parallelism nowadays is created by loops. Right? You have a loop that you have 10,000 elements, and you want to do the same operation on each of the elements. Add 5 to each of the elements. How do you parallelize that? You parallelize that by just chunking that up into pieces and giving one of the pieces to each of the CPUs. And that allows you to speed up things because each CPU has to do only a part of the work. And so the overall time you spend on that particular loop is reduced optimally by the number of cores you're using to run that thing. Right? If you run it on 10 cores, you hope that it will be 10 times faster. It will not, and I will show you why. But the thing is that these bars you see are those loops. And the gaps in between is what happens at the end of the loop. When all the cores kind of go towards the end of the loop. And you might think that I have 64 cores on my machine, they all run the same speed. No, they don't. Because of phase of moon, thermal differences in the cores, which causes the operating system to change clock rates on each of the cores independently. So there are different speeds and a lot of factors that influence that the amount of time spent on the equally sized chunks on the different cores are actually different. Some cores take longer, some of the processors are faster. That means that you always wait for the slowest guy, because you have to wait for the slowest guy, for the last one to finish before you can go on from your parallel loop, right? You have to wait finishing. And that is why you're seeing these gaps. Because of synchronization overhead that is needed at the end of the loop. And the more cores you have, the higher that synchronization overhead. This is the second reason why we started to look into HPX. Right? Because they said, oh well, we use only half of our machine essentially. Right? Half of the compute resources are utilized. Not everything was. 60% we use only. So that's why we came up with HPX. Does that make sense? Okay. So let me show you another real-world example from parallel computing. So what we have here is a graph which shows you how much speed up I can get, how much faster I can run when I run a parallel loop on 64 cores. So I have a loop which does as a large array of things where the x-axis is the number of elements in the array, power 2 to the power of whatever is here. So starting from 32 elements to, well, something like 1 billion elements here. 2 to the power of 29 is half a billion. Okay, 500 billion. So a graph. And what you see here is the dependency we measured on a real loop that tells us, okay, when I have a very small number of elements, I have essentially no speed up at all. The blue line means 1. That is what the sequential execution costs. And only when the number of elements grows, we actually see some speed up over the sequential execution we had before. Right? And don't worry about that up and down over there. That's completely irrelevant effects. So I put that dotted line there so you can see that for very large elements, it actually gets close to 64 times faster because I have 64 cores. Now, this curve was collected with a loop that does a lot of computation inside the loop body. A lot of trigonometric computations or some floating point operations. A lot of stuff is going on there. Now, this line shows you the same where you have essentially no work in the body. Well, all you do is adding 2 integers. Very, very small amount of work in the loop body. And you see a completely different picture, right? The question is why? Why do I see one behavior in parallel loops when I have what's called a compute-bound computation, where the overall speed is limited by the CPUs, against where I have memory-bound computation, which means that the overall speed of the computation is limited by the amount of data that is moved through the memory buses. And that's the two kind of limitations, main limitations we have in modern systems. So anybody any idea why we see that different behavior? Completely different behavior? By the way, these vertical lines are the cache lines, the cache sizes. So you see that when we get out of L3, we suddenly get a big drop of here. Well, everybody knows what the cache is in the machines? No idea? Have you taken, well, you should take architectures, the architecture class. Really. Have you taken architectures already?
It's 30s.
So you should know what a cache is, right?
I just can't remember exactly which is L1. L1 is the most.
L1 is the closest one to the CPU, it's the smallest one, the fastest one. L2 is kind of a bit further away, and L3 is far, far away from the CPU. But still faster than main memory, because that is the speed you get when you work out of main memory. That's why it's dropping off, right? Because the whole thing doesn't fit into the cache before. You have 500 million elements, we don't fit in. Up to, I don't know, 100 million elements, things still fit in the cache, so we see that speed up, and then we see the drop. But anyway, why is that behavior completely different? What's your guess? Well, I kind of hinted at it. I said one has a lot of work to do, the other one does only a little work.
Overhead.
Right. And we'll get to that. Another thing that is interesting, this is the same graph just for different number of cores. So the blue line here is what you see when you run on 2 cores, and the brown line is when you actually run on 64 cores. Okay, so you would think that all of them get a speed up of 2 when you have at least 2 cores, right? So just let's look at that a bit more. You see that for different number of cores, you have completely different behavior in terms of speed up you can achieve on the same amount of data. Again, overheads. We can talk about that in more detail if you're interested. So I'm not going to bore you with all of this. The short story is all of these things have caused us to start thinking about how we can actually expose that to the user, and how can we overcome all of that. So, how does parallelization work? when you parallelize code. In the simplest case, a loop. How does that work? As I said, you have 1 million elements, and you just split that 1 million elements into pieces. You have 10 cores, so each core works on 100,000 elements. And that gives you speed up, hopefully, because, well, each of the cores that work concurrently have to do less work, right? Not 1 million ones, but only 100,000. So the theoretical speed up you should get is 10, if you have 10 cores. But just for the record, on GPUs, parallelization works completely different. Because there, on CPUs, you have one CPU that works on a chunk on 100,000 elements. On GPUs, you have one GPU core that works per element. So if you have 100,000 elements, you essentially use 100,000 cores on the GPU to do that in parallel. So it's a completely different parallelization scheme. And I don't want to go into that. So one of the things we use in HPX heavily is what we call futures. And that is kind of the main thing that allows us to overcome these strides I showed in the beginning. So let me tell you what a future is. And if that is the only thing you take away from my talk today, that is more than enough. Anybody has read the Hitchhiker's Guide Through the Galaxy? You have read it. You have read it. You have read it. And you probably have laughed your ass off, right? Because it's hilarious. So you really should read that. Or at least watch the movie with the robot, Marvin, who is deeply depressed. Depressed robot. It's just fun. You should read it. Anyway. That's the reason why everybody, whenever you need an integer in programming examples, everybody uses 42. You know the story about Hitchhiker's Guide Through the Galaxy? The thing is that some foreign civilization knows everything, and they have come up with the problem that they need to figure out what is the meaning of life, universe, and everything else. They really want to understand what is the essence of life. And nobody can answer that question. So they build a computer, and that computer they call Deep Thought. And they asked Deep Thought after they built their computer, hey, what is the meaning of life, universe, and everything else? And Deep Thought says, I need 7.5 million years to compute that answer. Please come back when I'm done. So Deep Thought goes computing, and they are very distraught because they don't want to wait for 7.5 million years. So they want to go on with their lives while they're waiting for the answer. And essentially, that universal answer stands for that function that Deep Thought has to calculate. But since you don't want to wait for it, you don't call that function directly, which would make you wait for it, right? You want to go on with your life and do other things in the meantime while Deep Thought is doing stuff. So the way in C++ you do that, you call a function which is called async. Give async that function, and async creates a new thread and comes back right away and gives you an object which is called a future, which represents the result that will eventually be delivered to you. Then you can go on with your life for 7.5 million years. You don't have to wait for that actively, because in the background that thing is churning. And when you are sick and tired of waiting, you call get on the future. And that get will do one of two things. It will either give you the answer if it has been computed, or it will suspend inside get and come back only when the answer is available. And this is a beautiful way of abstracting threading from you, because you don't see any threads anymore. You don't see any multiprocessing anymore. All you see is do this and tell me when you're done. And that future concept is absolutely central and crucial for writing code much more efficiently. By the way, futures have been invented in Java in the 1970s. So just to give you an idea that something good has come out of it. Something good. Then futures were forgotten for 25 years, 30 years. Like everything new is just good forgotten, well forgotten old stuff, right? So futures have been reinvented in the early 2000s. Actually, we were kind of instrumental in bringing that back on the agenda. That's important stuff. Yeah, I will shut up in a second. Okay? Just take away that futures are crucial and will help you to manage parallelism. So whenever you think of using a thread explicitly, hey, pthread create, right, to create a new thread, don't do that, because threads don't allow you to reason about things. This allows you to reason about the parallelism that is going on. And that is one of the abstractions, right? We talked about abstractness in the beginning. That helps you reason about parallel code. So, as I said, if nothing else, take away that asynchronous programming and futures is what you should do when you want to do parallel computing. So, I'll shut up because somebody just interrupted me because of the pizza. But I'm happy to talk to you about other things while we eat. So, okay. Yes?
Is there a reason why we pass a reference to the function and not the function?
It's not a reference, it's an address. I just made it explicit that the address is being passed. But you can remove that ampersand and roll it as well. It's just for brevity. So I'm using pointers. Don't tell anybody. Okay?
So you know in a lot of other languages, they have a very similar, like, almost black box-like interface to handling threads. So for example, like React.js, it handles all the rendering.
Python has it.
I think JavaScript does as well with async.
Yes.
I was wondering if that's advised for programmers to an extent.
Well, as I said, the beauty of that is this works also if you run on one thread, on one physical underlying thread. Because all you do, you schedule a function that to run on that thread eventually. And JavaScript is a good example because JavaScript is one thread. But you have full asynchrony there, and you do these things in JavaScript, and it still works. But you can do it on many threads as well, which allows you to concurrently execute this. In JavaScript, essentially, what happens is that when you actually ask for the answer, that thing is being computed in the background. So the execution of that function starts only when you actually ask for the answer. That's why it just works. Yes?
If you led with this performance graph in the beginning, how does this one compare?
Well, that one allows you to squeeze it.
Just squeeze it a bit.
Squeeze the things, because you can overlay things better. Right? You can do things asynchronously and not have to wait for the barrier. Or while you're waiting for the barrier, you can do other stuff in the background. So you can utilize your resources much better. Well, the graphs I showed, I didn't reveal where that comes from because you want to eat pizza. But at some point we can certainly sit and I can explain. It's too late already. So, any other questions?
So I'd also like to ask for any advice or tips when it comes to debugging thread or parallel programming.
Use a debugger that is decent and allows you to do multi-threaded debugging. And GDB is definitely not the debugger to do that, because it's horrible. I mean, it works kind of, but I use Visual Studio on Windows. It's definitely the best development environment you can get.
I'm talking about like practices in regards to like race conditions or other things that kind of pop up when it comes to parallel programming.
Experience. It's the only thing. Beat your fingers bloody until you get it. That's the only thing you can do. There is not much I can tell you about that. You know, the problem is to recognize race conditions because they are not obvious. And if you look at code, you seldom see them explicitly, especially if you don't know how they look like. But over the years, you get kind of a sense of what to look for when it comes to race conditions. It's very difficult to debug usually. If you're lucky, you get a segfault the moment you have the race condition, then the debugger will point you to the place where things are happening. There are tools available that can detect race conditions. Things like Valgrind and the sanitizers and GCC and Clang can definitely help you with that. But they usually just point you in the proximity of where things are happening, not at the actual point where things are happening. The problem with race conditions is that they might have more, might not, depending on what the sequencing of the threads is, right? When the threads run independently, there's no race condition. It only happens when two threads happen to run in a certain way, time-wise, that they access the same variable at the same time and write to the variable at the same time. Right? That's when the race condition happens. Or one writes and the other one reads, which can be a race condition as well. So you have to protect these sections of code appropriately to make sure that only one thread runs through it, or use atomics or other techniques that allow you to prevent that. Yeah, just to summarize, if you're interested in C++ or parallel computing or high performance computing, I'd be more than happy to talk to you. Just come by, find me. Or take the operating system class, which is, by the way, pure C, so you will hate it. But okay, thank you. Thanks, Ian.
So I think we brought 2 meat lovers and then 2 cheeses. Let me just